Hello, today I'm going to look at how to solve the LeetCode problem redundant connection. First we're going to look at a problem description and give an example. Then we're going to look at the union find data structure, how to implement it, what is path compression, and finally the code for it. Then we're going to look at the union find solution to the problem, give an example, give the code, and discuss the time complexity. First, what is the problem? You're given a graph, and you have to remove one edge to make this graph a tree. A tree is defined as a directed acyclic graph. For example, you're given this input, where 1 is connected to 2, 2 is connected to 3, and 1 is connected to 3. You see, if you remove 2 connected to 3, then you get a tree. So you return 2 and 3. The union find data structure has two primary operations, find and union. Every element in the union find is part of a group. In this example, every element's group is a color. For example, 1 is blue, 2 is 3, and so on. The union operation merges two groups together. The find operation gives the group of an element. In this example, if we union 1 and 2, 1 joins the orange group. Alternatively, we could make it so that 2 joins the blue group. Now if we union 3 and 4, 4 joins the red group. Now if we union 1 and 4, all the elements from one group goes to the other, so 1 and 2 become red. Calling the find method on 3 returns red, because 3 is part of the red group. Calling the find method on 5 returns black, because 5 is part of the black group. Now let's look at how to implement the union find. Each group is a number from 0 through n, and each group is resembled by a tree. Calling union on two groups adds one tree to another tree, or adds one group to another group. For optimization, the smaller tree is added to the larger tree. The find method goes up in the tree until you hit a root, and the root is the group number. In this example, if you union 1 and 2, which in this case is 0 and 1 because it's 0 indexed, you add 1 to 0. Now if you union 0 and 2, you add 2 to 0. Now unioning 2 and 3, you add 3 to 2. Calling find on 3 comes from 3 to 2 to 0. So the group number is 0. As we saw in the last example, this isn't very fast because you have to jump multiple times to get to the root. This is not slow right now, but could get very slow with large inputs. So we use a technique called path compression. Path compression compresses the tree so that each root is directly connected to its child, so that there are only two levels in the tree. In this example, to compress this tree, we connect 0 to 3. The path compression is done every time the find method is called on that tree. Now let's look at the code of the union find. First, we initialize the class. This array called parent gives the parent of every node. In the constructor, takes in the size, and we initialize the parent array with the size. For each element in the array, we give the parent of that as itself, which is the initial state of the array. Every node's parent is itself. Every root's parent is itself. Next, we make the find method. The find method takes in an element and returns the group number. If the parent of that element is the element, it is a root, because that's what we did in the constructor. So we return that element. Otherwise, we set the parent of that element to the root, which is doing path compression, and then we return the parent of that element, which is now the root. The union method takes in two elements and doesn't return anything. We first find the roots of the elements using the find method, and then if the roots are the same, we do nothing since they are already in the same group. Then we set the parent of the first root to the second root, essentially merging the two trees. We have this utility method called sameGroup, which takes in two elements and returns a Boolean. It returns true if both the elements are in the same group, and we do this by checking if the roots are the same. Now let's look at the union find solution to the problem. We first iterate through each edge. If the nodes are part of the same group already, then we return that edge as the answer. Otherwise, we union the two nodes. In this example, we're given the graph 1 connected to 2, 2 connected to 3, and 1 connected to 3. We first look at the edge 1 connected to 2. They are not part of the same group since 1 is part of the blue group and 2 is part of the red group. So we union those two groups. Now we look at the edge 1 connected to 3. They are not part of the same group, so we union those two groups. Now we look at the edge 2 connected to 3. They are part of the same group right now, so we return 2 connected to 3 as the answer. Looking at the code, we first have this initial driver method. Then we add all the union find code, including the find method, the union method, and the sameGroup method, also the parent array. All of this we discussed earlier in the union class. We initialize the parent array with a size of edges.length plus 1. Now we actually implement the logic of the problem. We iterate over each edge. If the edge values are the same, we return that edge. Otherwise, we union both those values. Note that we do -1 because in the problem we're given 1 through n, but since arrays are 1 indexed, we want 0 through n and -1. Outside of the loop, we can return null because we know that it'll never reach that. Every union find method has a time complexity of O of 1. It's complicated of why it's O of 1, so I won't discuss it here. In the problem, we iterate over all n edges, so the resulting time complexity is O of n. Thank you for listening, and I hope you enjoyed.